So today we're going to do a lot of basic probability and basic counting. So I'm going to start with the game of tic-tac-toe. Have we talked about tic-tac-toe yet in this class? No? Okay. Just in the interest of full disclosure, I am the champion at the Williamstown Elementary School playground. I have yet to be defeated. I have been tied once, but I have a truly impressive record against kids aged 5 to 13. Okay? Why am I so good at tic-tac-toe versus these little kids?
There's a way you play that you can't lose.
There's a way to play. How do I find that quickly? How do I adapt on the fly? So, how many opening moves are there? Are there in tic-tac-toe?
9.
9. How many responses?
8.
Okay, so already after just 2 moves, there's 72 possible game states. So one possibility is, how many total games are there of tic-tac-toe?
9 factorial.
So one possibility is to say that there are 9 factorial games. I claim, however, that there can't be 9 factorial games. Yes?
You rotate the board.
Oh, no. Even before we do that. Why aren't there 9 factorial games?
We're not going to be using all the squares for every game. Some of them blend much faster.
Okay, so why won't we use all the squares?
Because once you start having a few plays, you want to start blocking, so it limits your amount
We
of
want to just farm 3 in a row faster.
Once you get 3 in a row, the game is over. Now, if you are playing on an elementary school playground, you may actually be forced to continue to play the game until all squares are filled. How many of you have ever watched a baseball playoff series? They have the best of 7. Once you've lost 4 games, it's over. They don't just play a couple more games. You're done. You go home. Okay? In tic-tac-toe, there are not 9 factorial games, because as soon as someone gets 3 in a row, it's done. In terms of writing a computer program to analyze things, it may not be bad to explore all 9 factorial possibilities. But once we have 3 in a row, we're done. So a nice question is, how many games of tic-tac-toe are there? This has been solved by many people, not surprisingly. It's a good thing to try to figure out. It's a good thing for people who want some coding practice to try to do that. We're going to attack the problem using symmetry. So symmetry helps computations. It's very important to answer the right question and not the question that is asked. Okay, I trust you can all read the book. I'm not going to go through all the different poker examples in the book. I'm happy to do that. I want to try to emphasize the fundamental insights, the ways to look at problems. When I'm playing tic-tac-toe, I just care about analyzing the game. How many opening moves are there really? 3. And what are those 3 moves?
Middle side, and corner.
Yeah. We normally call it center, corner, and then middle. That's it. If I move in this corner, I can rotate. And then it's or here, or here, or here. They're the same move. So in terms of trying to analyze the paths of tic-tac-toe, there's really only 3 opening moves. How many responses are there? How many? 2. So there's only 2 responses here. I can go in a middle, or I can go in a corner. How many responses are there here? 5. So that would be the first response, the second response, the third response, the fourth response, the 5th response. And how many responses are here? 5. So first response, second response, third response, fourth response. Does it matter which one I call 1, 2, 3? Not at all. So how many possible first two move sequences are there in tic-tac-toe up to symmetry? 12, which is a lot smaller than 72. So this really cuts down on the analysis. This is why I can do so well, and adapt on the fly to whatever the kids are throwing at me. There's not that many paths to look at. So in some sense, what I'm claiming is the following two games are the same. So in game 1, I start here, and over here I start in this spot. Then the person responds here. Do you want to count those games as the same or not?
You do.
I do. But it makes the problem of counting how many games of tic-tac-toe are there a lot harder, because this is now considered the same. You have to now worry about how many times do I have symmetric games of this occur. And so depending on what problem you have, it may be easy to count things one way rather than the other. This is one of the key things to keep in mind when you're doing stuff like this. Any biology people here? So one of the things I am known for on campus is playing with Legos. I will talk more about this as the year progresses. These are supposed to be two identical bricks. Okay? And a really good question in Lego theory is how many ways are there to combine a certain number of Legos? In the original Lego patent, they talked about 6 2x4 bricks. In the interest of making this a reasonable calculation, I'm going to not allow things at arbitrary angles like this. I will force the angles to either be a right angle or 180 degrees. So, if you start looking, this is one possibility. I can start moving things up. Is this configuration like this the same as this configuration? So I just turned it around. Is that considered different? It shouldn't really matter how I'm holding it, but in terms of doing the analysis, it could make a difference. There are some things where you can only do these rotations by rotating in 3 spaces if you're doing something on a plane, or 4 spaces if you're doing something in 3 dimensions. So you may not actually be able to physically do the rotation where you stand. If I want to go for these two games are mirror images of each other. I can flip this by flipping through 3-dimensional space and make this game the same as this game. But if I live in flat world, I can't do that flipping. And you have to then ask yourself, will you allow yourself to do something like this? This is called, I think, chirality in biochemistry, that you can have 2 compounds that are mirror images of each other. I've seen one person shaking their head as a yes, so I'm doing a good job. And one will kill you and one will cure you. And so a mirror flip could be very bad. So again, the big takeaway from all of this stuff over here is know what you're trying to count. And depending on what you're trying to solve, what you want to count may not be your initial instinct. Okay? At the end of the day, I only care about winning in tic-tac-toe. A better person wouldn't want to be this competitive against little kids, but I feel they have to learn. Okay? And so for my purposes, I don't really care about how many distinct games there are of tic-tac-toe. I care about just equivalence classes of games. And this is how I want to attack the problem. Okay, any questions on tic-tac-toe? So this was from page 114. All right. If there are no preferences, what I want to do now is I want to move on to a little bit of poker hands. Typically when I teach this class, there's usually at least one person who is taking this because they want to do better at poker. Okay? One of the most important things to remember if you do want to apply this to poker is I am not responsible for any losses you accrue, but for any gains, that is definitely a result of my class and should be remembered. The other thing to take into account is in poker you calculate probabilities of hands. If you add wild cards, the probabilities of certain hands change. And you have to take that into account. Depending on what people have declared, the order of hands may not be what you thought. So here's a good question. What is the probability I have a pair of kings in a 5-card hand. All hands equally likely. Is this a well-posed question for a math stats class? Okay, now the question is, how do you interpret this?
Should be any pair.
I'm sorry? Any pair of...
It doesn't matter if it's kings or queens or anything.
I don't like queens. I like how the king works.
You could have one pair of kings, or you could have 2 pairs of kings. You haven't specified.
So one thing is I could have 2 pairs of kings. I could have all 4 kings. What if I have 3 kings? Would that count? So in some sense this is saying not that I have only 2 kings, but that I have at least 2 kings. So you've got to be very careful when you write something like this. Out of curiosity, how many people interpret this as, if you have 3 kings, the answer to this question would be no, you don't have a pair of kings? If you're playing poker, you would not call 3 kings a pair of kings. You would call it 3 of a kind. It's a higher hand, it's worth more. From a mathematical perspective, though, if you have 3 kings, you also have 2 kings. You also have 1 king. Alright? So we could do the probability that we have at least 2 kings, or the probability we have exactly 2 kings. Let's do exactly. We have exactly a pair of kings. So the number of hands with exactly 2 kings. I've got to form a hand of 5. I have to choose 2 of the kings. There are 4 possible kings. I choose 2 of them. How many cards are left to choose from?
48.
Why 48?
We don't want to accidentally choose
We don't want to choose cards from the kings. If I had written, I have 50 cards remaining, and I choose 3 cards to complete my hand to 5, this would be wrong. And the reason this is wrong is I could choose more kings. And I could get up to 3 kings. I don't want to have any more kings. This should be 48, choose 3. How many hands are there with 5 cards? So how many ways can you choose a hand of 5 cards?
52, 5.
52, choose 5. And so now if I want the probability, all I have to do is just draw a big division line. And that's the probability. So this would be the probability of exactly 1 pair of kings in 5 cards. I might have another pair. I don't care about that. All I care about is that I only want to have 2 kings. I don't want anything more than that. How would you calculate the probability? Yes?
Can you explain the 3?
Sure. I need to have 5 cards total.
Oh.
Right?
Yeah.
And so I've already chosen 2 of my cards to be kings. I have 3 remaining cards. There's a lot of good features about writing it like this, and I'm actually glad you got me back on this. The 2 plus the 3 equals the 5. I have 5 cards I have to distribute, and I'm distributing them in 2 different ways. And I'm not allowing myself to draw from the same region twice. Here I'm drawing 2 from 4, 2 from the kings, and here I'm drawing 3 from the non-kings. This is very similar to the Williams-Amherst example from last class. Okay. Let's say now I want to calculate the probability I have at least 2 kings. How would we do that? Is the answer, first I choose 2 kings, and now the remaining cards, well, it's okay if I choose more kings. And then I divide by 52 choose 5. What do you think? No? Why not? This makes sure I have 2 kings, and then I don't care if I get more kings afterwards. Does this seem reasonable? Seems reasonable. Can anybody give me another answer? Another way to calculate this?
1 minus the probability that you get no kings minus the probability that you get 1 king.
Good, so 1 is actually probability of no kings and probability of 1 king. And so that would be 1 minus, it would be no kings, and then 52 choose 5, plus 1 king, and then 48 choose 4, divided by 52 choose 5. Yes?
Wouldn't it be 51 choose 4?
Wait, over here?
Yeah.
No, because I want to make sure I have exactly 1 king. This is, the probability I have at least 2 kings is, I find the probability I have no kings. I find the probability I have exactly 1 king.
Then the
Wait,
other
shouldn't that be
is
48?
52 choose
Oh.
5.
48 choose 5?
No,
Because you don't
Oh,
want to draw any
sorry, yes,
kings.
you're right. Yes, that should be a 48. Absolutely. Absolutely, yes. And you can tell I'm wrong because 52 plus 4 is 56. That's higher than the 52 down here. I have too many cards at registers. Absolutely. If I really cared, I would ask OIT to edit out that minute clip that we'll leave this in. So yes, I subtract off the probability I have exactly no kings and the probability I have exactly 1 king. You could also do it as the probability I have 2 kings, 4 choose 2, 48 choose 3, plus the probability I have exactly 3 kings, 48 choose 2, and then the probability I have 4 kings, 4 choose 4, 48 choose 1, divided by 52 choose 5. Yes, I know 4 choose 4 is 1. I like to write the 4 choose 4 so I can see what's going on. 4 plus 1 is 5. 4 plus 48 is 52. By being a little bit pedantic and writing this, it makes it easier for me to follow what's going on. This has given us 3 answers. If you do the calculation, it turns out 2 of the 3 answers are the same. Which 2 answers do you think are the same? Yeah, there's probably a reason why I'm writing these 2 underneath each other over here, and this one has been put off to the side. So the question is, which one do you think is right? Do you think this is the correct answer, or these 2 over here? These 2 really are essentially the same calculation. This is just using the law of complementary events. How can you tell which one is right?
Well, for this one, you're going to be double counting cases where you choose a certain, like, let's say we choose the ace and diamonds in the 2, we choose spades here. Is it the same as choosing, like, I forgot the suits, clubs and spades here and diamonds there?
So I mean, you could be specific. You could say maybe the king of spades, the king of diamonds are the 2 ones I choose here. And then for my next 3 cards, maybe I choose the ace of spades, the 2 of spades, and the king of clubs. Or I could choose the king of clubs and the king of spades. Oh, sorry, the king of diamonds. And then over here, the ace of spades, the 2 of spades, and then the king of diamonds. So this hand is counted twice. It's counted once where the king of spades and the king of diamonds are the ones that were chosen as my kings. And it's counted once when the king of clubs and king of spades. Is there any other way that this hand is counted?
If you choose the king of diamonds.
Yeah, if I choose king of diamonds, king of clubs, and then ace of spades, 2 of spades, and then king of spades.
So what you were saying earlier, can you just tell because there's 54 up on?
As a rule of thumb, yes. Because this adds up to 54, your spider sense should be tingling, something's wrong here, almost sure. There is another way to tell which one is right. Or at least to have a very high likelihood of determining which one is right. What could we do to determine which one is probably correct? If somebody had called me, we would have had free munchkins. Go straight with my phone. Yes?
Write some code.
Write some code, which will lead in beautifully to Wednesday's class. When you have something like this, and you have 2 different ways of calculating things, write a computer code. Choose a bunch of cards randomly, and just see which probability is it converging to. If you run 1,000 hands, should that be enough? Probably not at 1,000. If you run 1,000,000, should that be enough? Probably at 1,000,000. You should be able to see the differences between these probabilities. So as an exercise, if you want to prepare for Wednesday's class, try to write a little code, and this is why I'm deliberately not doing these calculations for you, to see which one do the numerics support. Does it support this, or does it support one of these? This is one of the reasons why it is so important to be able to write code for stuff like this. It's very easy to make mistakes. Sometimes you'll also drop factors. And sometimes you'll see that your answer differs from maybe the numerical simulations by approximately a factor of 2 or 3 or 6. And that probably means you dropped a coefficient somewhere. So sometimes the numerics can actually help you guide what the answer should be. Okay. Any questions on this poker hand problem? So we will use Mathematica in class on Wednesday, so I'm not giving you any written homework this week, so you have plenty of time to go over and do some practice coding. There's a Mathematica, I think about a 20-25-minute video that's posted online, as well as a Mathematica template to just practice. If you want to program in R, in Python, in almost any language you want, that's fine. Whatever language you're comfortable with is perfectly fine. We're not going to be doing any extremely hard computations. Whatever language you're familiar with is fine. We'll often talk about pseudocode to handle problems like this. But this is the 21st century. If you cannot just do some quick simulations, you're in trouble. Okay. Any other poker questions, any other poker problems people were particularly interested in chapter 3? Okay. We will have the first bridge lunch this Thursday at noon in Mission and West Cafe. If anybody hasn't emailed me and wants to be on the email list for this, let me know. We're actually going to play an easier version of Whist on Thursday, and then we'll move to Mondays for future lunches. Typically when you play bridge, there's a very complicated bidding process that goes on, and most of the time a suit is chosen to be the special suit, to be the trump suit. And in some sense, this is the most important suit there is. So the way bridge works is there are 4 players named North, South, East, and West. North and South are a team, East and West are a team. Cultural trivia question. Who were the 3 wicked witches? I'm sorry, who were the 3 witches in Wizard of Oz? Yes.
West, East. Oh, those are the wicked ones.
Those are the wicked ones. Yes, very good. And?
Oh, and North.
And North. North was the good one. Who was the one who was killed first, the East or the West?
Yes.
I don't remember, so if it's East, you get the extra credit and email me. I remember it was the West and the East were the bad ones, the North was the good one. And you don't read the South one until later. So North and South are partners. And let's say North and South declare spades as trump. Optional hearts. I think I used hearts in the book. So they declare hearts as trump. And let's say the way bridge is played is once you declare, whoever bid the suit first, their cards are kept secret, and the other person's hand is exposed for the entire world to see. This is still an advantage to you because you know, if let's say you're South and you're the declarer, you know North's hand, so you know exactly what your opponents have. You don't know who has what, but you know exactly which cards you're missing. For the opposition, West knows exactly what cards are not in his hand and the shown hand North, but doesn't know if it's on West's team's hand or West's opponent's hand. So let's say we have 8 trump between us. So how many are we missing?
5.
We're missing 5. So the question is, how are the 5 missing trumps split between West and East? This is a really good question. Knowing how likely these different splits are, this affects how you play. If you have 12 trump between the 2 of you, do you know how the trump is split among the remaining people? Yes. You may not know who has it, but you know there's only 1 trump missing. Either West has the trump or East has the trump. The more trump that are missing, the more complicated things are. And this affects how you play. And so, to practice for today's lecture, I actually played 2-handed bridge with my wife last night. The distribution's a little bit strange in 2-handed bridge. I actually had 8 trump and I knew of a missing one that was 9. My wife unfortunately had every run that was missing, and all my calculations sadly failed. So this is not going to guarantee success, but it will allow you to play the odds. And we want to know, what is the probability that we have all 5 trump in one hand? That could be disastrous for us. So we want to know the probability it splits 5-0. Okay? So there are 5 missing trumps. All right? Let's say we're missing the ace, the 2, the 3, the 4, and the 5. For definiteness. Why am I choosing these as my missing trump values? Be more specific than just...
Because it doesn't matter.
It doesn't matter, and this makes it very easy to talk about. You know, I want the numbers 1 through 5. What's the probability that East has the ace? That East has the 2? That East has the 3?
Half also.
And 4 is a half, and 5 is a half. So the probability of a 5-0 split is going to be 2 choose 1, because I have 2 players who could have all 5 trump, times 1/2 to the 5th. So that would be 1/2 to the 4th, or 1/16. Does that seem reasonable? Are there any other ways we could try to calculate the probability of a 5-0 split? So again, whenever you can calculate something multiple ways, calculate it multiple ways. Does this seem like a reasonable model? Each card has a 50-50 chance. And so it should just be 1/16. Yes?
Another way you could calculate it is if you're doling out 26 cards.
Okay.
That probability, like, that you choose all 5, and then the rest of the 13 hands for one person.
Good. So, method 2. So, I have 2 choose 1 ways of choosing the person. Right? Either East gets all 5 or West gets all 5. So let's say I choose the person who's going to get all 5. I choose East. They have to get all 5 of the remaining cards. 5 choose 5. And now, how many cards are left? 21. And how many do they have to get of the remaining 21? 8, because they have to have 13 cards. The 52 cards are split evenly among the 4 people. Alright, so now the question is, what are these numbers? So I printed out the part from the book, just so I have numbers on me. Alright, so this is equal to, so if we calculate the probability, we have to divide by what? This is the number of ways of one person getting all 5 cards. I want to know the probability. So what do I have to divide by?
26 choose 13.
26 choose 13. Alright, so when I do that, I get approximately, forgive me for not memorizing the number. Oh, actually it's exactly, okay. Everything cancels and get 9 over 230, which is about 3.91%. Okay. Anybody know roughly what 1/16 is? I'm sorry, not that. 0.0625, I think. 1 divided by 16 is 0.0625. So this is approximately 6.25%. Alright. We don't know which answer is right, but we know at least one of them is wrong. Unfortunately, is it possible that both could be wrong? Yes, that's actually not eliminated by the analysis here. It's possible both approaches are wrong. What should we do? Simulate it. When in doubt, write code and simulate it. That's the best thing you can do for something like this. And when you simulate this many, many, many times, it turns out your answer is going to be extremely close to 3.91%. This is going to be winning. It's not going to be 6.25. These numbers differ by a significant amount. Simulations will detect the error. Yes?
So why is that method wrong?
That's a good question. So this is one of the fun things about teaching probability, is I can try to sneak things past you. So I must have made a false assumption somewhere. What is the assumption that I've made that's wrong?
That the probability of a trump card going to one hand to the other doesn't matter on how many cards are already assigned to that hand.
Good. Basically what we're saying is each specific card has a 50-50 chance. That is correct. But the more trump cards I've assigned to this hand, the less likely it is for the next card in the hand to be one of the trumps. Because there are more non-trump cards left. If you want to think about it, there's lots of different ways of doing the calculation. So there's 13 spots here. There's 13 spots here. This is east, this is west. Let's say we give the ace of, we take the cards one at a time and we're assigning them. And we give this person the ace of hearts. What's the probability we gave this person the ace of hearts as opposed to this person? 50-50. There are 26 free spots available. And 13 of those free spots lie in the east. Now we have the next trump. What's the odds that this person gets the next trump?
12 over 26.
I'd say 12 over
25.
25. That there are 25 free spots left. This person has more open spots. So I go through even more of an analysis of this in the book. But that is essentially what's going on. That's where the error is assuming that these are all independent events. They're not independent events. The more cards you have, the harder it's going to be to fill it. Okay? The other thing is, as you've probably learned by now, is I love extreme examples. I think you can learn an enormous amount from extreme examples. So let's go to ridiculous extremes. So let's say there are 4 trump, and you want to have 2 in each hand. Once you have, let's say it's the ace, the deuce, the 3, and the 4. What's the probability my first player gets the ace of hearts? The 2 of hearts. Half. 3 of hearts, a half. 4 of hearts, a half. Let's say I give this person the ace of hearts and the 4 of hearts. What's the probability that this person gets the 3 of hearts? 0. There's no space left. I can't expect the probabilities to keep staying a half all the time. I filled up this person's hand. There's no way this person can get the 3 of hearts. Okay? So there are dependencies that are going on. Dependent events are much harder to analyze. Okay? And so the difficulty is that we have to be breaking this up into cases. Okay. Any other questions on the trump distribution problem? Okay. What I want to do now is I want to go back and do a little bit with the binomial theorem, because we will be needing this later in the semester. So I do apologize. It was pointed out to me yesterday. Yesterday means after last class, that when I asked people if they'd seen the Pascal's triangle, and everybody said yes, I forgot to ask, have you heard that the coefficients in Pascal's triangle are the binomial coefficients? And a lot of you had not heard that. So let me just quickly go back to Pascal's triangle. So we have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. There are an enormous number of phenomenal properties lurking in Pascal's triangle. A lot of them lead to very interesting computational challenges. And so I'm going to save some of this for Friday. I'm not expecting that many prospective students will be coming to this class on Friday because this is a 300 level probability class. But there could be people who misread the title and think that this might be a lower level course. So I'm trying to leave at least some accessible material for Friday in case we have people wandering in from high schools. It also is a great way to talk about the difficulty of writing efficient code. For a lot of things, the computers are so fast now, you don't have to code well. It's very different than when I was an undergraduate. When I was doing my thesis, I was working in the library. And my bosses let me use the library computers on the weekend as long as I showed up early Monday morning to free up the computers for them to use again. Because I needed a lot of computations being done. Now it would take me maybe 2 or 3 minutes on my computer to reproduce what I did over weeks. It's amazing how computers have changed. And you can be a little bit inefficient now. But for some things, efficiency matters. And we'll see on Friday some coding related to Pascal's triangle. So it turns out that the nth row is the coefficients from expanding x plus y to the n. So you get n choose 0, x to the n, plus n choose 1, x to the n minus 1, y, plus dot dot dot, plus n choose n minus 1, x, y to the n minus 1, plus n choose n, y to the n. So this is what you get when you expand out x plus y to the n. We'll talk in a moment as to why these binomial coefficients occur there. But these coefficients occur when you expand out x plus y to the n, and these are the coefficients in Pascal's triangle, and they satisfy this beautiful relationship that each number is the sum of the ones above it. If I want to do this one over here, if you want, I need to almost view that I have a 0 over here. And so if this one, I can write this as n choose, so this would be 2, this would be 2 choose 0, this would be 2 choose negative 1, and this would be 3 choose 0. How many ways are there to choose no objects from 2? One. There's one way to do nothing. How many ways are there to choose negative 1 objects? There's no way. Okay? You cannot choose negative 1 objects. You can talk about, I have 4 ice cream bars. How many ways can I choose an ice cream bar to eat? There's one way to choose an ice cream bar to eat. You cannot somehow create an ice cream bar coming out of you. Okay? We can interpret choose negative 1 as 0. And if we do that, if we view almost like an infinity of zeros lurking over here, then the formula still holds. And this tells us that this is a good way to view what's going on. So what I want to do now is I want to prove why Pascal's triangle works. These are key building blocks. We've seen these binomial coefficients. We've seen these n choose k in the poker hands we've been looking at, in the bridge hands we've been looking at. So much follows from these binomial coefficients. We want to have a sense of their properties. So we proved by story that n plus 1 choose k plus 1 is equal to n choose k plus n choose k plus 1. And we did this by looking at n plus 1 people, n from Williams, 1 from Amherst. You can view this as 1 choose 1, 1 choose 0. I have the person from Amherst, I don't have the person from Amherst. Normally you don't write 1s in equations, it makes things a little bit cleaner not to write them, so normally we drop that. Okay? So let's prove the binomial theorem. So we need to expand x plus y to the n. Out of curiosity, how many of you have seen a proof of the binomial theorem? How many of you have not seen a proof of the binomial theorem? Okay, so a good number of you have not seen the proof. When we expand x plus y to the n, the way you should view this is x plus y to the n is I have n factors. X plus y, x plus y, x plus y. And in each factor, I choose an x or I choose a y. What's the highest power of x I can get? Sorry? N. What's the lowest power of x I can get? 0. So we know the powers of x range from 0 to n. Powers of x and similarly y range from 0 to n. If I choose 5 powers for x, how many powers for y do I have? N minus 5. And sum of x, y powers is n. This is very similar to the other relationship we proved, that n choose k is the same as n choose n minus k. The number of ways to choose k people to get the star on their belly and be a star belly sneech is the same as the number of ways to choose n minus k people to exclude. And so here, if I'm choosing x 5 times, then that means I'm choosing y n minus 5 times. So the first thing we know is that when we look at the expansion, it's got to be a sum of polynomials in x and y. So x plus y to the n has to be a sum, k goes from 0 to n, of some coefficient, which is going to depend on n and k, times x to the k, y to the n minus k. It's got to look like this. I can't have a power of x greater than n or less than 0, and the sum of the power of x and the sum of the power of y has to be n. So my polynomial has to look like this when I expand. Okay. Now I just need to figure out what is a and k. Well, how do I get a term x to the k, y to the n minus k? I chose k x's, and I chose n minus k y's. So if I have n factors, how many ways are there to choose k factors from n to give me an x? I'm sorry?
And choose k.
And choose k. How many factors are left? Now that I've chosen k factors, how many factors remain? N minus k. And I have to choose all of them to be y. Alright, what's n minus k choose n minus k?
1.
It's 1. Most of the time people would not bother writing this. Just to highlight what's going on in the proof, I'll write it here. And then we'll just say, oh well, this just equals n choose k. And so the answer is x plus y to the n is the sum, k goes from 0 to n, of n choose k, x to the k, y to the n minus k. And that's one of the proofs. Okay? So, yes?
Should you go over why a is the number of ways of choosing x?
Sure, because I've got to get a term x to the k, y to the n minus k. How do I get this term when I'm expanding out this product? To get an x to the k means in the n factors, k times I choose x. To get the y to the n minus k, I have to choose y n minus k times. And so really it's from the definition of the binomial coefficients. Now, if we define the binomial coefficients like this, we don't actually know that n... I will not go too far aside. I will stop there. Is this the same as what I wrote earlier? Yes?
The role of x and y is
The role of x and y is flipped. What I actually wrote over here is if you come all the way back, look at the camera did move. If you come all the way back, I wrote n choose 0 x to the n. What I have there is I have n choose 0 x to the 0. It doesn't really matter, because you could do things the other way. Instead of doing it as x to the k, I could do it as x to the n minus k. And this would be the same as the sum of a and k, x to the n minus k, y to the k. K goes from 0 to n. It's completely symmetric. And then that would give us then the sum, k goes from 0 to n, of n choose k, x to the n minus k, y to the k. Any questions on this proof of the binomial theorem? There's two more things I want to do in the binomial theorem, just because this is such an important result, and then that would be a good place, I think, to call it a day. So I'll leave Pascal's triangle. I think I killed some of it. Oh well. So another approach is proof by induction. I'm going to just sketch the idea. Let's say we know x plus y to the n is the sum, k goes from 0 to n, of n choose k, x to the n minus k, y to the k. Then x plus y to the n plus 1 is x plus y times x plus y to the n. So this would be x times x plus y to the n plus y times x plus y to the n. And so now what we can do is we can take what we had before, and so we have over here now this beautiful relationship. Well, we have this expansion for x plus y to the n. We can plug that in. The x is going to bump up all those x's by 1. The y is going to bump up all the y's by 1. And then we can look and see what would be the coefficient of the x to the n minus k plus 1 term. So now substitute and simplify. So at this point now it's going to become a bunch of algebra. But we would have x plus y to the n is going to be the sum, k goes from 0 to n, of n choose k, x to the n minus k plus 1, y to the k, plus a sum, k goes from 0 to n, of n choose k, x to the n minus k, y to the k, plus 1. And now we want to somehow combine them, and now notice that the sum of the powers is n plus 1. So this must equal a sum, I'll use a different letter. I'll use a different. L goes from 0 to n plus 1 of a, l, n plus 1, x to the n minus l, y to the l. And now all you have to do is do the algebra and figure out, let's collect terms. And in the relationship we had before, connecting each element is the sum of the one to the right and to the left above it. That's what's going to prove that this is the binomial coefficient n plus 1, choose l plus 1, from binomial relation. So I'm not going to go through all the algebra details of this. I think it's in the book. If not, I'm happy to chat with you about how you would do a calculation like that. There's lots of different ways of proving a result like this. Okay? But at least now we have this result. And then we have about 1 minute left, and so I wanted to just end with a situation of where might you have seen this. So this is going to be, we're going all the way back to Calc 1. So Calc 1. So function, derivative. What's the derivative of x squared? 2x. X to the 3 halves. 3 halves x to the 1 half. and then x to the square root of 2.
Root 2x to the root 2 minus.
The way you prove these results is very different. So for proof, this one uses the binomial theorem. You expand out x plus h squared. Or more generally, if you want to do x to the n, you expand it out using the binomial theorem. If you want to calculate x to the 3 halves, you can't use the binomial theorem because that uses an integer power. What you have to do is you say, if f of x is x to the 3 halves, look at g of x is f of x squared, which is now going to be x cubed. You can now take the derivative of g and solve for f prime. If you want to calculate x to the root 2, you have to first even figure out what does it mean to raise something to the root 2 power. And it turns out you use the exponential function. X to the root 2 is e to the root 2 the natural log of x. And then you have to use the chain rule. So just give you a sense of where all this stuff is used. The binomial theorem is looking in the background for something over here. Alright, so this is a good place to stop.